We would like you to introduce you to our project named XLogic, which is composed of two devices. One that replaces everything you see right here into a single device. It is called digital logic circuit and replaces 6 logic gates: NAND, AND, OR, NOR, XOR, and XNOR, and 2 kinds of flip-flop: the flip-flop and JK flip-flop. The second device is our tester, which is a digital logic probe that can tell the user whether a signal is high, low, or high impedance. Both of these devices are based on the microcontroller unit from Microchip, PIC16F13145. So let's see how they work, shall we? What we have here is a very simple circuit to demonstrate how our XLogic digital circuit works. So right now we can see that it's powered and the LEDs are off. Now, in order to operate our XLogic, first we have to select what kind of gate we need. For that, we can press this single button to toggle between these functions. Let's try the first function, which is a NAND gate. Now, NAND gates are very simple devices. They have 2 inputs and the output works this way. So if both inputs are high, then the output is going to be low. So let's probe first the first input. Here we have 1. The second input is also 1. So our output is going to be low. But if we change one of the inputs, we can see that the output then becomes high. Now let's check the second function, which is an AND gate. AND gates are the exact opposite of the NAND gate, and they only are going to be high if both inputs are high. So let's check. The first input is high, the second input is high, then our output is going to be high. But if we change that, we can see that the output then becomes low. Now our next function is a NOR gate, and the output this time is placed right here. And NOR gates are quite simple. If any of the inputs are high, then the output is going to be low. Right now we have both inputs as low. So if we change that, we can see that then the output becomes low. The next function is an OR gate. This time the output is placed where it was before. And OR gates are quite simple. If any of the inputs are high, then the output is going to be high. So right now we have 0 because both inputs are low. And if we change that, then the output becomes high. Our next function is exclusive NOR gates, and this time the output is placed right here. And in the case of exclusive NOR gates, if both inputs are the same, then the output is going to be high, and if they are different, the output is going to be low. So right now both of them are low and the output is 1. If we change both of them to high, then the output is high, but if one of them is low and the other is high, then the output is low. Now our next function is exclusive OR, which is the opposite of the last one. This time around, if both inputs are different, then the output is going to be high. Right now we have one input as high, the second one is low, then the output is high, But if both of them are the same, then the output becomes low. Our next function is a D flip-flop, and in this case we have 4 inputs, which are clear, data, clock, and set. And we have 2 outputs, which is Q and not Q, which is the opposite of the first one. So the way this works is if we check at the output, we can control it directly with the set and clear functions. Right now is low. So if I toggle the set function, we can see that the output becomes high. If we want to change that, we can use the clear signal and it's going to low. Now, if we need to change it using the data and the clock signal, the way this works is that the output Q is going to follow the input data, but only when there is a rising edge on the clock signal. So if we set data to high, we can see that the output is not changing until we apply a clock signal. So I'm going to set data to low, the output remains high until I set the clock signal. And the last function is a JK flip-flop, and it has 4 input signals as J, K, clock, and clear, and it has 2 outputs in the way of Q and not Q. And the way this works is if we are to set the Q output, we just need to set J and clear K, and then send a clock pulse like that. If we want to clear the output, we could potentially use a clear signal. We could also clear J and keep K high and send a clock signal like this. We can also toggle the outputs, clearing, setting both J and K, and then sending a clock signal, and with that we toggle the output. Or we can keep the output the same by clearing both J and K, and the output remains the same. And that's all the basic functions of our X logic. You can use both of them to better understand digital electronics, and hopefully you can see that they are very useful in replacing a lot of many circuits within a single one.